In zdaj gradimo naš dogodek naprej, se ne ustavljamo in skupaj bomo prisluhnili predavanju, ki bo osvetlilo enega izmed ključnih izzivov današnjega časa. To je že večkrat tudi danes omenjeno recikliranje betona in vprašanje, kako lahko beton postane del krožnega gospodarstva. In the lecture, Dr. Carsten Rieger, concrete expert from Sika Services AG, presented the current challenges and solutions that enable the recycling of concrete and much more. So, Dr. Carsten Rieger, welcome among us, and the stage is yours.
Thank you very much for the kind introduction, and it's also a big honor and pleasure to be here and to discuss with you topics about concrete, especially concrete recycling. So I'm based in Zurich, and I'm working for an international company. So I'm traveling a lot, and I'm discussing a lot with people about the future of concrete, about potential of recycling, and also what I want to discuss with you today is kind of bring you a little bigger picture from the beginning, and then give you one example from the city of Zurich, how they do it with recycling concrete, and then show you at the end a process that Sika developed also to enhance the concrete recycling in the market. Basically that's it. What I'm talking about. So when we talk about these aspects of the recycling, there are three major points. One, of course, we are all aware. All our in our business, in the concrete business, we need to reduce the CO2 footprint of the concrete production. I think everybody is clear about that. The world needs more concrete in the future, because due to the megatrends, urbanization, we need more infrastructure, we need more high-rise building. We saw an example that it's also possible to build high-rise building with wood, but there is still concrete needed, and so that is very clear from the megatrends that we will need concrete in the future. At the same time, we need to find solutions how we can bring down the CO2 footprint of this material. When we look in many countries, we see a shortage of materials that we need for concrete, especially high-quality sands and aggregates. And on the other hand, when we look at the right side of this, what we do with our concrete structure when we don't need them anymore, we tear them down. But in many countries of the world, we just use that for landfills. So and this is I think we could also see that as a raw material and try to think of how can we reuse this waste as we now treat it. So that's the situation at the moment. The cement production is quite CO2 intensive. That's how it is. Of course, the cement industry is working on reducing that very heavily. That's quite clear. We need a lot of sand and aggregates for the concrete production, and but at the end of the use of these building is really end of life of this building material that is so CO2 incentive. So this is the sand and the aggregates. This is the major part of the concrete. Roughly 2 tons per every cubic meter is sand and aggregates. So that looks quite nice. That is also in many countries we still have enough resources of that. But when you look what we need worldwide, which amounts, you see on the left side, you see the cement production. It's roughly 4.2 billion tons yearly on cement. You see China has a major part of this. And you see it's now a little bit flattening, and that's because of China. And on the right side, you see the annual production of aggregates. This is 41 billion metric tons of aggregate is needed every year for the concrete production. And many times we just look at the cement because this is so CO2 intensive with the production, but the transport of the aggregates, this is also a very big point. You know, when you Google a little bit, you find a lot of articles about the scarcity of especially sand, high quality sands. And that leads to a lot of transports, because when you have not the right quality of sand in your country and you need to build a lot of concrete structures, you need to import sand. And what does that mean? A lot of transports. And they are also very, very CO2 intensive. So what could we do? We could also take a look what is there and maybe use the old concrete that we don't need anymore as a source for new concrete production. So when you look at the world and you try to find out how much concrete demolition waste is there available, it's really hard to find figures. You often find figures about CDW, that means construction demolition waste, and this is everything included. So this is bricks, this is wood, this is steel, and this is concrete. And then you can look at these countries, how much of this material is really reused, and the figure is quite small. So there is a huge potential. Of course, when you compare this number now that is somehow available, 600 million tons of concrete demolition waste, and you compare this to the 41 billion that is required, this is ridiculous small, but I fully believe that there is much more of this. It's not just we know of that. And we know a lot of countries that have a lot of space there. They use the space for landfill, for using the old concrete for landfill. But I think there is a big potential. Yeah? So at the moment, this looks like waste. This is very clear. This is a waste of a construction site. But you see more and more site that this material is treated somehow. This is sorted, and this is the key of all the recycling, that you need to separate materials, make them available. I now want to give you a little example of the city of Zurich, how they see it. So the next slide, I have the kind permission of the city of Zurich to use them. So this is how the typical construction demolition waste looks like in the city of Zurich. So you see there is a certain part of wood. There are some metals inside. There is some glass inside, some steel, but only a few. But the biggest part is the concrete demolition waste, and it's the mixed material. And the mixed material is containing bricks and cementitious material. And so the city of Zurich, they want to use they want to reuse this material, or most of this material, again. And this is a big challenge. So how could they do it as a city? And why do they have to do this? So basically, the city of Zurich has a strategy to come down to a maximum energy consumption per citizen per year of 2,000 watts. And you see at the graph that started in the year 2000 at 6,000. We are now at the year 2024, so we are about roughly 4,000 when we are on track. But it's still double the amount that is the target. It's 2050, we could say. It's a long time there, but you need to make now the incentives or to get there. And and this is also, the CO2 emission per citizen should be reduced to maximum 1 ton per person and year. This is, of course, everything, but also a big impact has the construction of the city. That means every building the city constructs, that is a part of that CO2 emission. And this needs incentives. So also one of these thing is to make an incentive for contractors, for concrete producers to go in a more circular way. So and this started already in about 2000, that you first need to have standards for this. So concrete production is highly regulated, and if you want to change now from natural aggregates to recycled aggregates, you need to have a standard for this. You need somehow to implement a QC of that, and that is why in Switzerland there is this regulation for recycling concrete and also for recycling aggregates. So basically what is in there is regulated applications for concrete using recycled aggregates. And by the way, recycled concrete in Switzerland means that at least 25% of the aggregates are coming from recycled concrete. So it's not just 5% there, it's 500 kilograms roughly of the cubic meter of concrete has to be minimum recycled aggregates. And of course, you need to somehow regulate the ingredients that you need to limit something, because this can have impact on the strength, on the durability of the concrete. That is clear. Also, when you extend a certain volume fraction of recycled aggregates, that has an impact on the E modulus of the concrete. So there are different classes. This is very important for all the specifier and engineers, that you have a basis for that is needed. So then the city of Zurich looked at the concrete, and they looked at the mass distribution of the concrete. I think we are all aware of that. And they looked at the carbon footprint of the ingredients. And basically what you see, and I think we are all aware of that, is that basically from the mass, it's the aggregates, that is clear. And but from the CO2 equivalent, that's two parts. That is the cement, and this is the reinforcement. So from a circularity aspect, the aggregates play the biggest role. From the CO2 perspective, cement and reinforcement. And reinforcement is really something also I want to emphasize here, because we are a lot of talking about the cement and reduce the cement. I think as engineers, we also have the responsibility to think of the reinforcement. Which reinforcement do we really need, and what do we just put on in there, because it's good to have it there. This also leads to a large CO2 footprint, and now we have a lot of sensors available on the market that could monitor the behavior of our structure, and maybe that can also lead to reduce a little bit our safety factors that we have as engineers. But this is just a side remark when I look at that figure. So coming back to the city of Zurich, what did they do? They said, okay, we look at the cement, and we now look at alternatives to a pure Portland cement. So they said, okay, when we look at the CO2 equivalent of a composite cement, we see we could save a lot of CO2. So they said, okay, a CEM 3B has a much lower value in CO2 equivalent per kilogram than a Portland cement. So and there, with that, they could reduce the CO2 footprint per cubic meter of concrete significantly. So what did they do? Basically, they said we want to tackle these 2 points, the circularity and the CO2 footprint. And how can you do it? You need to specify this. So the city of Zurich said in the year 2002 that all public buildings need to be built with recycling concrete, since 2002. And since 2015, all new public buildings need to be built with recycling concrete containing CEM 3B. So that is a must. And that resulted in some pre-tests done with contractors, with recyclers, because you need to make sure that you have enough material available when you specify this. It needs to be available. So some recyclers around Zurich needed to be in the boat, and the contractors and the ready-mix producer to produce a certain quality of that material. But the decision was very, very quickly done, because it was already in 2002, and short time later the first buildings were produced. For example, this is a public school building in Birch. It's built in 2002, and the recycling concrete was 60% already, and also used for pre-stressed ceiling there. And it's still standing today. One of my daughters is going into that school, so it's all good. Huh? It's all working. There are other examples. A public housing estate in Zurich, built in 2006 with already 75% of recycling concrete, and is also used for earthquake resistance walls. So this is also possible. And then another public school, also in Zurich, there the amount of recycling concrete is already 95%, and it's containing the blended cement CEM 3B. So that shows that this is possible, and you need to start somewhere. I always say it, walk the talk, and you need some people who just take the ownership and do something. I think we have enough good engineers in the world who can judge about the risks for such a material, and we have now a certain need to do something. When you look at the concrete consumption in the city of Zurich per year, the yellow one is the recycling concrete, and the gray one is the normal concrete. So over the years, you can see roughly 80 to 90% of the concrete that is required from the city. That's only for public buildings. You have some peaks because you need to renovate, you need to rebuild something. Is built with recycling concrete. There are some limitations for some applications. That's why we have some normal concrete still there, because you cannot use the recycling concrete for everything. But it's 80-90% is used, and 80% of this is used with CEM 3B. So that has a big impact. It's not just a specification, and this is really done in Zurich. That resulted to 30,000 tons of CO2 reduction in 2022, and this is equals to 30% of the CO2 released due to building materials. So that has a certain impact. So now I want to come to a process, because you still have these peaks with gray material, and this is I showed you the standard. So the recycling concrete is not allowed for every application, because it has some limitations, and so I want to introduce you to a process that eliminates these limitations or these disadvantages. So one of the disadvantages of the recycling material is that when you crush concrete down to several parts, you can classify this according to the size. You can make your sieve curve for the concrete. That is fine. But the main difference to a normal aggregate is the porosity, because you have an agglomerate of aggregates and the cement stone. And the cement stone is highly porous. That means you have a complete different water absorption. So the water absorption of this recycling material is by far higher than of primary aggregates. And this causes a lot of problems. So one problem is, for example, when you use a lot of this material, you need more water in your concrete. When you put more water in your concrete, you have a strength problem. So what you have to do to maintain your strength, you need to increase your cement content. That leads to a circular aspect. You can say, okay, with a recycling concrete, I have a circular concrete, but your CO2 footprint can be slightly higher than a normal concrete. So why should you do it? Huh? So that's why we thought about a process of how to separate and clean even further. And we call the process recover, because it has several aspects. One aspect is the circularity, the recycling, and another aspect is the CO2. But first, the basic idea of the process is that we take the concrete demolition waste, still called waste. We could also call it material, because it's a raw material. And basically we put it into our process. Our process, I show you later a video of this, is basically a big ball mill. And into that ball mill we put the concrete demolition waste, and we drive the ball mill not in a way that it's usually driven, because usually it's driven to mill something down. We don't want to mill it down. We want to introduce a lot of friction, that we separate the nice stones from the cementitious parts. So it's basically, like a steel brush, we want to clean the aggregates, because we want to take out the primary aggregates and give them the properties back that they had at the beginning. That's the idea of the process. So at the end of the process, we have the aggregates, we have the sand fractions, and we have the separated cementitious parts in a powder. And that is basically the outcome of that. And again, why do we do that? This is because we want to reduce the water absorption of these aggregates. And by reducing the water absorption, by cleaning them, we can open this field much more, that everybody can use recycling aggregates to produce concrete with a lower CO2 footprint. So basically, and these were first lab results, you see here the different fractions of aggregates on the x-axis here. You see the gray line is the primary material. You have some water absorption of the very fine particles. It's between 0 and 1%, and the red line is the water absorption of the recycled aggregates. So this is between 6 and 8%, significantly higher. So with the process of the recovery, we want to bring that down as much as possible. These are lab results, first lab results. So that was the first idea. Said, okay, if we can bring that down, we really can extract the primary aggregates out of the recycling concrete. That was the idea. And then the idea is then that after the demolition, we take the material, we process it through the recover process, and can bring it back as primary aggregates and reuse it again. So, the other story is, you see some more errors there, that we also can introduce CO2 into the process. And this is the second aspect, the CO2 and recover. Because when you grind, or when you put the friction and you have this powder, this can be very fast and easy carbonated. So the CO2 reacts really fast with this powder, so we can bind CO2 in this process as well. So we can have the circularity aspects by cleaning the aggregates from the cementitious parts, and we can have the CO2 sequestration part, which is much, much faster by combining it with a grinding. So basically we can create with this a circular economy of concrete. We are saving natural resources because we are taking out the aggregates again from the concrete. We can use this process for CO2 sequestration, so bind CO2 into that. And with that, we can reduce the cement fraction of the recycled concrete, and we can also use the powder to partly replace cement. So that maybe sounds nice, and you would ask, okay, does it really work? So we ask ourselves, does it really work? So we had to show it also on a larger level, not only in the lab that this works. We talked to recycler, and they said, we are talking about big amounts, and also one thing was the fluctuation. So if I tear down, a normal house that is maybe 80 years, and on the next day I have an infrastructure, an old bridge is maybe 30 years. This is not the same concrete. So what do I get? And so that was the reason why we installed a pilot plant, and we installed it not at the Sika facilities, we installed it at a recycler, because we really wanted to see how this process behaves with real material, real recycling material. So here is a short video about this pilot plant that you can see how it works and what are the parts of this plant. So the idea was first that we install kind of a mobile plant. So it's in 4 shipping containers. And the idea was that we bring it from customer to customer, but in fact we only moved it once, and we saw it's much easier to bring the concrete demolition waste to the plant than the plant to the concrete demolition waste. So what you see here is the hopper. This is where the material gets filled in. So this is an example of pre-crushed concrete demolition waste. You see here it's pre-crushed down to smaller than 40 millimeter. But this is how it's done in every case because of transportation. They crush it down that you can fill much more into the trucks. So then the material gets transported into the heart of that plant, which is the ball mill. Here you see the ball mill, and there the material is separated. At the end of the ball mill, the coarse material falls out, and the finer particles are blown out and taken out with the process air. Of course, we as admixture producer, we tried several process aids to improve the process, and this is the CO2 that we also supplied to that process, that it reacts immediately with a powder. So as said, the process air, as it has some CO2 inside, we need to reuse again. So we have some filters there that filter out the powder material from the process air, and this is then collected separately. In the pilot plant, we also have a big air conditioning unit, because we wanted to play around with the humidity and the temperature to have some learnings about the process. And at the end of the process, you have on the right side you see the big bag here where we collect the powder material, and on the left side is where the coarse material comes out, and then it's separated to whatever fractions you like. Now we do it with a Swiss or European fractions. It's the sand is 0 to 4 millimeter. It's then 4 to 8 millimeter, 8 to 16, and 16 to 32. But you can, it's a normal seeding flour. You can do whatever you like. So that's basically it. There are of course some security measurements as we are dealing with CO2. That's very clear. But there are of course also some learning. We now produce or we use this plant now for more than 2 years. So we have some experience and some learnings with that. Together with a recycler, and one learning, for example, is to separate these two processes. So the step one is really the mechanical process where we separate the materials. It's just a pure friction, and we clean the aggregates and separate the powder. And then the step two is optional. So we can just take the powder and put the CO2 in contact with them. Why did we do that separation? Because of several reasons. One reason is that if you work with CO2 in a continuous process, because the step one is a continuous process, continuous material in and continuous material out. And when you put CO2 inside, you should make it somehow gas tight. But a continuous process, it's really hard to get it gas tight, I would say impossible. So we also had some CO2 leakages, and the CO2 is a high valuable material that you don't want to just leak out. So that is a technical aspect. Second technical aspect is for the separation of the material, you need a very dry environment. And for the carbonation, you prefer a rather wet environment. So you always need to come to a compromise, which is not good for the separation and not good for the carbonation. So when you separate it, you can focus on each step and have the perfect conditions. And also the third point is that you are much more flexible, because for the first step, the main thing what you need is the concrete demolition waste. And for the step two, the main thing what you need is CO2. And in many cases, you don't have these two materials not at the same place. So step one, we get out of that sand and aggregate in quality compared to primary material, and we get the uncarbonated powder. And then is the question what to do with that powder. So one option for sure is to bring it to the step two, to bring it in contact with CO2, to have the CO2 sequestration, because you have this powder, which is very fine, roughly maximum size to 100-120 micrometers. So you have a lot of surface. When you put the CO2 there, it reacts immediately. The reaction time of that is roughly 15 minutes. So when you leave it half an hour in the reactor, you have it completely carbonated. But the question is, do you need to carbonate this powder, or are there maybe other options? So I show you some test results. So for example, you can also use the uncarbonated powder as a filler material immediately for concrete production. No problem at all. It's basically an inert material. Let's say we assume that the recycled concrete is more than 20 years old. So we assume that it's completely reacted, the cement phases. So this is then an inert material you can use as a filler material. But there are maybe other materials. So the properties of that material, be it carbonated or uncarbonated, are more or less the same. That carbonation has no effect on some activity of that powder that was unfortunately not detected. That would be very nice if there would be some activity, but in fact it's not. So, but what did we get? So I want to show you some results of that. Some pictures to see. So on the left side, in the gray area, you see the input material, and for better comparison, we sieved it, and maybe you see the best with a 16-32 with a coarse material. You see on the left side is clear. You have a lot of cementitious material around the aggregates, and on the right side you see the material, how it comes out of the process. So of course we want to have the lowest water absorption. That is the target. So that means that we do not want to crush the aggregates, because when you crush them, you get some rough surfaces which require a higher water demand. So we want to keep the surface area as low as possible. That also can mean that we still have some agglomerates, and you see it here, that we still have some cement stone in between the aggregates, but you see clearly the cleaning effect. What we measured all the time is the water demand. So you see on the top left, you see the water demand of the aggregates, again, from small fractions to large fractions, and you see the red line is the input material that we take and measure the water demand. So we basically measure the water absorption of the aggregates after 24 hours. This is what we do. So you take the aggregates, you dry them, you put them into water, you surface dry them, and you measure the difference in weight. That we do with the input material, and that we do with the output material of all batches, and then we get after 2 years, some average values. So what you can see is that for all the fractions in average, we could reduce the water absorption by 50 to 60%, so very significantly. And when you look at the values, and that's the feedback we got from concrete producers and contractors, below 4% that somehow you can handle, but more than 8% or between 8 and 10%, that's far too much. Of course, what we do is, and that's the diagrams on the right side, is we change the granulometry. You don't get the same granulometry as you put in, because we have the large aggregates. They are agglomerates of smaller aggregates and the cementitious material. And when you separate them, you get a different granulometry, so we get much more fine contents. So when you look at the bottom of the right side, you see the particle size distribution with the output material, and we get roughly 20% of that is powder. So powder is defined what is transported via the air, and this is roughly, smaller than 120 micrometer. This is the powder. Then we get a big fraction, 50% is the 0 to 4, so this is the cent fraction, and then roughly 30% is coarser aggregates. Then in the pilot plant, we did the combined step 1 and step 2. So we put the CO2 in the process, and there, in average, we could sequestrate 15 kilograms CO2 per ton of concrete demolition waste during all these trials that we did. That is also an important figure. Now let's have a look at the powder. So again, there you see the particle size distribution, and you see the majority is below 100 microns. And what is also interesting is the chemical composition, because we have a lot of calcium oxide in that powder. That's clear. That's a cement stone, and interesting is the calcium oxide and the silicium oxide. So the silicium comes from the aggregates, so you still have some dust of the aggregates from the friction. That's clear, but the calcium oxide is quite significant, and this could also be a potential source for the cement production, because basically what you need for producing clinker is a calcium source. What we use as a calcium source is limestone, calcium carbonate, and then by heating it up, you separate the CO2 of the calcium carbonate, so you come to calcium oxide, and here you have calcium oxide directly as a source. So you don't need to separate the CO2 in the kiln, and that separation, the chemical decomposition of the limestone, that is roughly 50% of the CO2 output of the cement production. So this could also be an interesting use of the powder. Of course, here we have to discuss about the amount of the powder that is available. That is another discussion, but this is a possible use for that next to the use of the filler material. One other aspect of separating these two steps, the step 1 and the step 2, is because when you put in the CO2 and you sequestrate CO2, you basically have the opportunity to get CO2 certificates for this because you bind CO2. And one key element of this is how to measure the bound CO2. And that is not so easy in the continuous process. So what we did is basically we made a thermographic analysis of the powder before sequestration and after sequestration, and there you can nicely see what happens. So the calcium hydroxide we can carbonate. You see the small peak that's disappearing after the carbonation, and the calcium carbonates are increasing, and also we can carbonate some of the hydrates that you see. You see there is still potential of carbonating more, but this is how we measure it, and this is a very important step because we are also with some partners developing a methodology of getting CO2 certificates for this, and there is a very key element is how to measure the CO2 that you take in that process. So, what is the status now? We after these learnings of the piloting phase, we always got asked, okay, so what are the costs of such a plant, and what do I need for that? So we partnered with a company called Semtech, based in Austria. They are experts in ball mills for the mining and for the cement industry. So they made us an engineering. We asked them to make an engineering of a upscale plant, 20 tons per hour throughput, and this is basically how it looks like. So the heart is still the ball mill. And what you see behind the ball mill, this is the filter unit of filtering out this powder. In the front, you see still the fraction, the coarser aggregates, the sieving tower, and the separation into different fractions. And you know, we have a fact sheet for that. So that means we can tell you now how much energy you need for that. How much space you need, how much manpower you need, and of course also what is the cost of that? What is the investment cost and what is the operational cost? Because at the end of the day, all this that stays a nice story until there is a business case for somebody to invest in that. That's very clear. So that's what we needed for that. So we have it for this 20-ton. Step 1, this is only the separation, and we also have it for the step 2 because then we developed a separate step 2 for that. So basically what we do is having a chamber where we put the powder inside and we put the CO2 inside and let it react, and then we can much easier measure the uptake of the CO2 by several ways. And also for that step we have a fact sheet with all the things that you need with CapEx and OpEx. That is very important. So and that is maybe an important message. That can be a nice opportunity, but this only will be used when there is a business case. And at the moment it looks like so. Who is paying more for aggregates? Because a recycler or whoever does it has to take the aggregates once more into his hands to clean them. And this needs to be paid. And he gets maybe a material that is 80–90% has the same properties as primary material. So who would pay more for a material that has still less properties than a primary material? That is a big question. The powder is a different story. That can be done maybe in a cooperation with a cement producer or with a mortar producer or whatever. There could be something, but for the aggregate, it's really a tough business. But so of course we did trials with these materials and just want to show you what could be technically possible. So of course we said, okay, can we use the aggregates that we get out of the recover process? So what we did is we had mix design, 300 kilogram cement, water cement ratio 0.52, and we did the same concrete using 100% primary aggregates, and we did the same concrete with 100% recover treated aggregates. So we are not talking anymore about 25%, we are talking about 100% replacement. Of course, we are an admixture company, so we could adjust a little bit of the admixture, but a concrete with 100% recycled concrete without the recover process is impossible. And that shows that this is possible. Using the recover, you can replace 100%. Another aspect that we looked at is the powder. So what can we do with the powder? And there is more the focus on our core business, which is the admixtures, is that we just said, okay, let's take a reference, 330 kilogram cement, water cement ratio again 0.52, and just replace 60 kilogram of the cement with the recover powder. So what happens if you do that? You could do it in two ways. You could say, I stay with the batching water, same batching water, then you have a much higher water cement ratio. So when you stay with the same batching water, you don't have issues with the workability, maybe not so much, but of course you have issues with your strength development. So your final strength will be reduced. So what you could also do is stay with the same water cement ratio. Then you have much less batching water, 140 liters. So who worked with 140 liters adding to concrete is a quite tough material. So you're struggling with the workability quite a lot. And you need something to compensate this. So what we did is we developed admixtures for both, because you know the workability issue, especially the slum keeping issue over time, this cannot be covered by conventional admixtures at the moment. So there we had to bring new technologies, and also and we strongly believe that this is the key for the future, is an accelerator, a special type accelerator that we use for these recycling materials, because you know this is where we see the trends. I show it from the city of Zurich that they use composite cement, so cements with less clinker, with less reactive material. And of course, the requirements will stay the same. The precasters will want to demold after a certain time. They want to use the molds. And also in winter time, you want to build your houses and demold, and you need your strength. So there will be a high demand of accelerators in the future, and we need to be ready for that. So have accelerator types for different clinker replacement materials. And this is where we are working on, and this is also where the recover process helps us to work on that. Another aspect of recycling concrete is the shrinkage aspect. This is also a result of the water demand of the aggregates. When the aggregates suck the water or work like a sponge, that results often in shrinkage cracks. So we looked at that. We looked at the autogenous shrinkage. So we measured from time zero when we filled the concrete, and we measured the drying shrinkage, which is from the Swiss standard. The measurement starts after 24 hours, but this is in the standard. So we measured two ways. And in both, we could see that when we replace the recycling aggregates with recover-treated aggregates, we could reduce the shrinkage significantly. And, of course, this enhances then the durability of the concrete. Because at the end of the day, when you have durability issues with your concrete, you need to replace it earlier. And from the whole lifetime, that doesn't make sense. So this is a very important aspect as well when we are talking about recycling concrete. So to summarize, and And maybe there is one thing to understand. So why do we as an admixture company go into that recycling? So we are not changing our business. We are not a recycling company. We are not selling machinery. It's just, we have the process invented. We have some patents on the process. Everybody can use that. And we want to partner up because we see that in the future, the recycling business is not done with just one party. It's a combination. You need to have, I would say, a really big table to put all the parties on the same table to discuss. And we want to be in the game, of course, at the end of the day with our admixtures. But this is something we can bring and we can put on the table. But we need a recycler, we need a concrete producer, we need perhaps somebody who brings a CO2. And of course, we need some incentives from the public sector. So you have a few parties already that need to be involved to make this happen. So what I wanted to show you is that there are opportunities to really increase the circularity of concrete. There are things that can be done immediately, like the example of the city of Zurich. They do it for 20 years now and successfully to really reduce the CO2 footprint of the concrete and increase the circularity. And this recover technology to go one step further to even increase more the circularity and reduce the CO2 footprint even more. One aspect is there, and that I see more and more in the countries, that I said it during my talk. One key point is to separate the materials. And when I'm traveling around, I see that I have huge amount of construction demolition waste, but this is not separated. And the separation has to begin at the demolition at the construction site. Otherwise, it's so expensive to separate all the materials that we cannot reuse all this. So with that, I would like to end, and thank you very much for your attention.